And here we go again. Have I got sound right? Yes, we have sound. I don't have the image I'm supposed to be having. That's better. Let's get that out of the way. Right, hello. I can turn this down a bit now. I've dug out my lapel microphone instead of having the stereo ambient. I know it only gives you mono sound now, but it should be much better quality. Not that you really want to hear me. But anyway, yes, hello. Today I'm going to have another look at this circuit that I was trying to debug and reverse engineer in Logisim. First off, a correction. I said it was for a compact portable last time. That was wrong. It's actually for a Sanyo MBC775. It's a very similar kind of idea, a portable computer. This one's full colour though. So that's what it is that I'm reverse engineering. Very nice unit. I wouldn't say no to one of those myself. But the board itself is this board here, where you've got 4 banks of memory and a load of control logic, and it's this part of it that I'm working on. The board normally has 4 banks of 64K of memory, the good old 4164 chips. This person wants to upgrade it from 256K to 640K, which means replacing these chips, but also reconfiguring the memory addressing circuitry to be able to support those bigger chips. He's changed the chips, but it's just treating them like 64s still. So we're trying to work out what it is in this circuitry that needs changing for the full 640K to show up. Now, for 640K on the PC and XT, you would normally change banks 0 and 1 to 256K chips. I've got the gurgles today. I've just had my lunch. So you'll have to excuse me if the gurgles are coming across on my lapel microphone. So yes, first 2 banks should be 256K each, and then the 64Ks to give 512 plus 128 is 640. Oof, goodness me. I can't stop gurgling today. Right, let's sit upright a bit more, might help. So what I've been doing, I've got the XT schematics here, and I've been comparing what they've reversed engineered from the Sanyo with what's in the published XT documents, and the Sanyo is based on the XT, so they should be very, very similar. So what we've got here is some what I think are probably problems with the reverse engineering. It's, as you can imagine from this picture, it's not going to be exactly easy to work out where things are connected to. So it's understandable that there'll be some errors in this reverse engineering. It's a pretty complicated and compact design. It might be a 4-layer board, but given the age of it, it's unlikely. But it certainly is a high density through-hole design. So yes, I think there are problems with this which are stopping me from progressing much at the moment. though I am getting a much deeper understanding of how it all works and how it fits together, especially from the XT schematics here. This area of interest here is the RAS-CAS decoding, which is what I'm looking at here. On the right hand side here we've got the CAS and the RAS outputs, which then come from all this address decoding logic. Now on the XT, and it's the same on the PC, a lot of the decoding logic is performed by U44, which is a ROM chip. A 4-bit ROM chip. So that is performing quite a complicated chunk of logic for the address decoding. On the Sanyo, that chip does not exist. It's all been done with discrete logic. Actually, on the original PC, that chip didn't exist either, because the original PC was 256K in 4 banks of 64. And if you wanted more than that, it had to be done on an expansion card. Once they'd introduced the XT, and in fact I think it's the 5155, which is the slightly upgraded version of the PC, then they introduced this ROM chip to do the address decoding to allow mismatched bank sizes. Because with the traditional ordinary Jelly Bean logic on the 5150, it was basically a case of cut the memory into 4 banks of 64 and feed it out to the chips. On the XT and the 5155, it needed more flexibility, because you could have 4 banks of 64 like on an old PC, or you could replace the first 2 banks with 41256s and change the address decoding to work with those. And that's what these jumpers on the XT do. They switch between just straight A14 and 15 going into this chip to all this address pins here for 16, 17, 18, 19 plus whatever planar RAM and RAM are going into the ROM chip to then generate these 2 outputs here, 10 and 11, which go into this 138 instead for generating the CAS signals. The RAS signals stay the same, I think, don't they? No, the RAS signals go from that 138, which, yeah, they come from the same decoding logic. So on the Sanyo, if there is the ability to upgrade it, then it will be done entirely in Jelly Bean logic, as far as I can tell. This is on WorthPoint, and WorthPoint is really annoying in that you can't easily get to the image for zooming in. What you have to do is go into the source of it and copy and paste the image, and then you can get at it. Right, now I can zoom in a bit. So on the XT, it's a 74510 PROM, programmable read-only memory. And as far as I can see, there is nothing like that on here. Oh, goodness me. No, there's lots of 74 logic series and not a lot else. And in fact, on this image, there are some chips on here which aren't even populated, which are in this reverse engineering, which must be populated on their version of it. So they probably made different versions of it. Maybe there's a version which has the upgradable facility on it, but this one doesn't. I don't know. I'm not that familiar with this model. So yes, it's finding the equivalent of this chip if it even exists. If it doesn't exist, then to upgrade the memory on the Sanyo is not really going to be possible without some major reworking of the motherboard. But yeah, things that bring up a red flag on this that say it's not correct to me are especially in the RAS signals here. These all come from the AND gates here, the 74S08, which are some of these AND gates here. And these are fed direct from this 138, which then has differing inputs to it depending on the address setting. But what we have here is some of the RAS comes straight from this 138, and some of it comes from this 157, and then you've got some of the 157 for the RAS coming from that 139, and then the AND gates don't go anywhere near the RAS at all. And the AND gates here are used for refreshing the memory. So that's going to be pretty much standard across the board. So I would imagine that the Sanyo would be doing it in the same way, but that's not what I'm seeing on this schematic. I would expect the RAS from... In fact, I'm thinking this here is actually the RAS signals, not this one. So these should be RAS, which then go straight into the AND gates, which then I would expect to go straight through to the RAS on the chips. It's possible that they've got the RAS and the CAS swapped over. It wouldn't make any difference as far as the chips are concerned when it comes to addressing them. What it would affect is how the chip refreshes. Because it's dynamic RAM, it has to be regularly refreshed to maintain its data. So either they have implemented the refresh slightly differently, so it refreshes using the CAS rather than the RAS, which is possible, or that's actually going to RAS and not CAS. And let me see, we've got 3 address pins here. There should be 4. Should only be 2 address pins, I think. So I've got a feeling that one of these would actually be this 5 volt here, or it should be this one here, which they've got labelled as A18. If that's A18, then that would be going from logic for this, but no, it can't be. Because if this is set up specifically for 4 banks of 64 at the moment, then that should just be going straight through into RAS, and that should be A14, A15 coming into here. So yes, it's exactly knowing what is coming in to these 138s and confirming that this U66 on here is actually U66 on here. Yeah. Yes, look, he's labelled this as 66 on here, and this he's tagged as U66 on here, but this is going through straight to the RAS through the AND gates. Here it's going through the AND gates, some of it into CAS and some of it through a multiplexer into CAS. And then we got some going through the same multiplexer into RAS and some not. I mean, it's possible that it's going into the multiplexer, but I would expect those AND gates to go into RAS, not into CAS. So that the refresh circuitry works properly. So if it does have the ability to upgrade, then because this is wired differently, because this is coming from Y4 to Y7 on the XT, but it's coming from Y0 to Y3, which means that that'll be wired for A0 and A1, with A2, which he's got labelled as A18, would be... hang on, no, what have we got? There's something here doesn't make sense, is it? No, that's right, no, see? Yeah, that would then be connected to ground on. A2 would be connected to ground on here, whereas on here he's got it connected to 5 volts. So it's the upper half, because that's on 5 volts. On this version, it's the lower half, because A2 must be ground. So what he's got labelled as A18 here looks to actually be, I would have thought, connected to ground. Unless it is A18 and it's just always having A18 as low. I don't know, this is confusing. If half of the, call these RAS instead of CAS, if half of the RAS and half of the CAS are going into a multiplexer, with these are the traditional 64K ones, which then go into here. Right, so this chip here must be selecting between 256K and 640K memory space by changing which RAS and CAS signals are getting through to the chips. So this, and it'll be affecting RAS 0, CAS 0, RAS 1, CAS 1, I think. Yeah, so these are labelled wrong, I think, on here. So output 0, that'll be RAS 0, which goes into multiplexer. RAS 2 goes into the multiplexer. CAS 0, RAS 0, RAS 1, CAS 0, CAS 1 go into this multiplexer. So what we effectively got is RAS 0A and RAS 0B, RAS 1A and RAS 1B, where the A is for 64K, the B is for 256K chips. And then this multiplexer is selecting which of the addresses is in use. Okay, so U93 on here is performing partially the same functionality as this 24510 ROM chip. So what drives the select logic on this? It's probably this unknown pin head here to choose, because I do know that this section here is wrong. I did query this with him and he did say yes, there was a mistake here, but we do need to check this section out just to see if that is actually connected to this jumper, in which case jumper closed will have one addressing scheme, jumper open will have the other addressing scheme. So that jumper there, by my reckoning, should switch between the addressing schemes. And it would be the lower bank, or the lower two banks would have 256K chips in them, and then the upper two banks would have 64K chips in them. But then we've got the other, because we've got the traditional 64K chip RAS-CAS generation here, and then this here is the 256K chip RAS-CAS generation. So you've got the 4 traditional RAS signals here. Then you've got the 2 extra CAS signals here and the 2 extra RAS signals here, which as well go through the AND gates for the memory refreshing. Right, that's making sense. So it all hinges really on the select signal of this 157, which would choose between the 64K or the 256K addressing. But until I get that properly mapped out, because there's no way this is connecting straight through to pin 14 of the delay line and to a jumper to ground and to 2 resistors, and that's just not right. I would imagine that you have 4.7K going to VCC, and it's got a delay line. It's just VCC in general. 4.7K on the select going to VCC as a pull-up, and then the jumper to ground to override the signal when you put the jumper on. So jumper off would be with S pulled high by the 4.7K resistor, and jumper on would be S pulled straight down to ground. So the 74 LS157, where are we? 74 LS157, 157. Which way does the select logic work on this? Okay. Nothing immediately sort of jumps out as saying when it's high you get A, when it's low you get B. Okay, in this function table here, oh, come back, with select, low for A, high for B. So when select is low, A is low, output is low. When A is high, output is high. So traditional is in A, expanded is in, sorry, no, we want 0 and 1. 0 would be A, 1 would be B, I expect on this. So for it to be for it to be B coming through, we need a select to be high. So jumper off would be 256k memory. Jumper on would be 640k memory, I think. That's JP6, which is, let's have a look. There's a J5, although this is, yeah, J5. No, J4. I would expect it to be somewhere around here. It could be that there. Can't see there's a component in the way, there's a capacitor masking the signal. Actually, thinking about it, we've got a better image here, haven't we? And it's still the same. Let's get a zoom in on this. Okay, I think it's here, but I can't tell because C103 is right slap bang on the ref des. It's an interesting chip. What's that one? 201JHT1006. Ooh, could that be a ROM chip that's doing the extra decoding or not? I don't know. I'll look that one up in a minute. Where are we? Yes, I'm looking for U93, which is here. The select pin is pin 1, which is coming down here and then disappearing under here. It might be coming down here, in which case, yes, it's going to that resistor, then to jumper that. Yeah, that is definitely wrong. That's going to that resistor, R22. R22, that'll then be going to VCC on that side of it. That's a, yeah, 470. It's a 47000 rather. 4700 red. And that'll be going to ground there. So yes, that jumper there I think must be JP6, which is going to be the jumper to select whether it's a 256k or a 640k system. And the 139 here is not populated. That's 92. Yeah, that's not populated on this board, which means this board, this specific version of the board, has no ability to go 640k. So it would be a case of fitting the 139. I think that's the only missing chips on here, is it? Now there's an S280 and LS158 up here. U45. U45. Ah, yes, that's this one up here, which is used as part of the improved address decoding. Which goes into A8 for those chips that want it. Where does pin 15 of this go to, I wonder? No chance of finding out. So that's not pin 15, pin 1 rather. Ditto, I've got no chance at all of finding out. Okay, but that's all part of the address decoding logic for the bigger chips. Has no effect on the smaller chips. U48 is an S280. Is that an LS280? I don't recognise 74S280. There is such a thing. 74LS280. Ah, parity generator. Right. Gotcha. Yeah, I know what that is. That's for the parity for which you would need these extra chips. So it's got no parity on this board, and that would be dealing with the parity. So yeah, that makes sense. That's got nothing to do with the expanded memory. So we've got the 139 there, and we've got the 158 there would need to be added. And there would obviously be some way, although no, that doesn't affect the smaller chips because there is no A8, it's the non-connected. So that's not going to affect that side of things at all. So just having that chip missing wouldn't affect the smaller memory. Having that chip missing is isolated by the mux here. So yes, so long as you've got the 139 and you've got the 158, they're installed and working, and you upgrade the memory in banks 0 and 1, which will be the ones connecting up the CAS and RAS from the 157 here. That's the 157 there. Which I would imagine these would be banks 0 and 1. Upgrade those ones, confirm that that is the ones connecting to the 157 to 256K chips. Connect that jumper JP6 to ground, and theoretically that should put it into 640K mode. From what I understand of the way this is all working. If that's correct, then I don't need to do any more work in Logisim, which is nice. If it's not, then I'm going to have to carry on working in Logisim. But I would need... I'm pretty certain that this is how I said on here, where you've got the select pulled up to VCC through the 4.7K and connecting to ground with the jumper. The enable pin is probably connecting permanently to ground. enable pin is hidden up here. 2, 3, 4, 5, 6, 7. So 15, that's 15 there. I can't see that anywhere at all, but that's probably, excuse me, going through a resistor straight to ground, is it? It'd be odd that they've got a resistor to ground, you just connect it to ground, but maybe, I suppose, but that's going to be one of these here, I suspect. Because they look like they're going to go to straight to ground, possibly, with that big chunky copper there. So yes, I think it's permanently enabled, probably. Oh, actually, it may not be permanently. Is it going to be permanently enabled? Probably. I don't see why it wouldn't be. Because the other RASs and CASs are permanently connected to their respective decoders here. So I suspect that E is just pulled straight to ground. S pulled up to 5 volts and linked to ground by JP6. So yes, to convert this specific instance of the motherboard, which is permanently set up to be 4 banks of 64K, it would be installing the 2 chips, the 158 and the 13, whatever it is, the 139 and the 158, and short JP6 to ground, and that should then allow banks 0 and 1 to be upgraded to 256K. So I think I've got to the bottom of it, but until it's actually tested and tried out, who knows? Who indeed knows? But the important thing is that it's only the first 2 banks that would be set up for 256K, which is the same as in the XT. Well, it's 256, 256, 64, 64. So I think that would be it for now. It's over to T Squared Productions, who's the owner of this, to try this out and report back. See if it can be just as simple as make sure these 2 chips are installed and working. JP6 shorted, and upgrade banks Norton 1 to 256K chips. And if you want parity as well, populate those 4 and add the S280. But it obviously isn't needed, and it's just wasteful really. Parity is it was useful when RAM chips were flaky, but reliability is so much better now. There's no need for parity. Right, well, I'm going to leave it there now, I think. Time for a cup of tea. And I'll see you next time I stream, which I'm not sure when that'll be or what I'll be doing, but best subscribe to or follow me on Twitch so that you get notified when I stream next. Okay then, well, cheerio.